We are busy with chapter 6 in the textbook of Cengel and Ghajar on the fundamentals of convection. We have made good progress. We've looked at the classification of fluid flow, which was a little bit of revision of fluid mechanics that you did last year, and then the velocity boundary layer, which you also did. Then we introduced the thermal boundary layer, which is very similar to that of the velocity boundary layer, the Prandtl number, the heat and momentum transfer in turbulent flow, the derivation of the differential equations, which you are doing also with Dr. Leroux, and then the solutions of the convective equations for a flat plate, and specifically the great work of Blasius, the non-dimensionalized convection equations and similarity. And today we are going to continue with paragraph 6.10, the functional forms of friction and convection coefficients. Okay, so paragraph 6.10, the functional forms. Okay, so the most important part of this paragraph of the textbook is that it actually shows that in terms of the fundamental equations, the continuity equation, the momentum equation, and the energy equation, there are three variables that in general needs to be solved. The velocity in the u direction, in the y direction, and as well as the temperature. And these equations can then be rewritten in a non-dimensionalized form so that you can actually show that the friction coefficient is a function of the non-dimensionalized distance x as well as the Reynolds number based on a characteristic length L. Similarly, the Nusselt number can be written as another function, but now of x, the Reynolds number, as well as the Prandtl number. So we can see that the only thing that is being added is the Prandtl number. Now, in terms of any body, we can get the averages by integration to show that in general the friction coefficient is one or other function of the Reynolds number always, and the Nusselt number is a function always of the Reynolds number and the Prandtl number. And later on in chapter 9, we are also going to show it is a function of the Grashof number, which is the natural convection. But let's leave that out for the moment. And this leads to the very, very important thing that in heat transfer, we in general can always write that the Nusselt number is equal to a constant, the Reynolds to a power n, as well as the Prandtl to the n. Okay. And later on in chapter 9, we are going to add the Grashof number to the power of p. But in general, at this stage, we are not going to introduce it. So the very important thing is that, and I'm going to refer to this quite a lot, is that the Nusselt number is always equal, can be written as equal to be a constant c, the Reynolds to the m, and Prandtl number to the n. So that is paragraph 6.10. Paragraph 6.11 is my favorite. This is about the analogies between momentum and heat transfer. So in general, in fluid mechanics and heat transfer, there are two things that we need to know. We need to know the friction coefficient, or the skin friction coefficient, and we need to know the Nusselt number. The moment we've got this, then we can normally determine the pressure drop. Pressure drop is important to us as engineers because you pay for this pressure drop because of a pump you're going to need, or a fan, or an aircraft engine that needs to propel an aeroplane. So we are always interested in the pressure drop. And of course, there are some cases where the pressure drop will be given to you, where you then need to determine the friction factor or the skin friction coefficient. With the Nusselt number, the moment we've got the Nusselt number, normally we can go and calculate the heat transfer. So that is why it is important. Now, going back to these equations, it is a little bit complicated, but you can go and work through it. One of the very important things that can be done is to say, let's look at the simplest cases. And the simplest case is where the Prandtl number is equal to 1. And there are many practical cases where this actually happens. Gases, in general, their Prandtl numbers are order of magnitude 1. 0.6 or 0.7 sometimes, and 0.8, maybe 1.1. But in general, it's a huge body of fluids that can be considered when we make this very simple assumption. Prandtl number is equal to 1. Now, this led to work which is known today as the Reynolds Analogy. And the Reynolds Analogy says that the skin friction coefficient divided by 2 is equal to the Chilton number. I'm going to define the Chilton number just now, which is then equal to the Nusselt number divided by the Reynolds number based on the length L, Prandtl number, and or you can write it as the Nusselt number. When you multiply the Reynolds with the Prandtl, you can actually write it as rho Cp and V. Not so important, but this is the very important equation. Now, yes, it's just another equation of many in the textbook. So what is so special about this equation? Well, it connects pressure drop, the fluid mechanics, with the heat transfer. The laws of nature says there's an analogy between the two. If you know the heat transfer characteristics, you can actually get the pressure drop characteristics. Or if you know the pressure drop characteristics, you can actually get the heat transfer characteristics. Now, this work has been developed a little bit further by other people trying to get solutions which are not valid only for a Prandtl number equal to 1, and that is known as the modified Reynolds Analogy and or the Chilton Colburn Analogy. The Chilton Colburn Analogy. And this analogy says that the friction coefficient multiplied by the Reynolds divided by 2 is equal to the Nusselt number based on x, Prandtl to the third, minus the third. Again, now the pressure drops, if you know this, you can get the other one. Can also be written, the details are shown in your textbook as the friction coefficient divided by 2 is equal to the Chilton x, Prandtl to the 2/3, and that is also known as the J factor, the Colburn J factor H, JH. So if you go and look through heat transfer literature, where pressure drops and heat transfer are important, and there are many practical cases where that is the case, then typically they will plot the J factor as a function of the friction coefficients. The J factor is another non-dimensionalized heat transfer coefficient. And this equation is valid for a much larger range of Prandtl numbers, larger than 0.6 and smaller than 60. So most fluids and gases actually will fall into this category, and therefore this analogy works. However, take note, it is for a flat plate only. Flat plate only. Now there's an example in your textbook that I'm not going to do because it is all written out. And I would like to show you schematically what this example is actually saying. It says that we've got a flat plate. And the flat plate is typically 3 by 2 meters. And we've got a fan that would ensure there's a velocity of 7 meters per second over the plate, with air which is at 20 degrees Celsius. And this plate is hanging somewhere, and there's a scale that shows the force on it. Okay, now in practice, of course, you're going to put the scale in there, and then because of the weight, it is going to show the weight of the plate. But if you then zero the scale, it would show nothing. But when you put on the fan, it's going to cause a pressure drop, and then there's going to be an increase or a decrease in what the scale is telling us. So from the scale, we can actually determine let's call it the drag force on the plate. But very, very importantly, what we can do is we can now go and say this drag on the plate is of course equal to the skin friction coefficient, the surface area rho v squared divided by 2. Okay. And from this, because we know what this value is, it was actually 0.86 newtons. It's equal to the skin friction coefficient. We've got the area, which is 3 by 2. The density of the air we can go and get from the tables. The velocity is 7, etc. So we can get the skin friction coefficient. Then we now make use of this analogy. Cfx divided by 2 is equal to the Chilton Prandtl to the 2/3. You can go and get the Chilton number. You can go and determine the Reynolds number. And from this, you can actually get the heat transfer coefficient. So the heat transfer coefficient, it is all in your textbook, is 12.87 watts per square meter degrees Celsius. There's another example that I'm going to do in more detail. That's why I'm going through this one very quickly. So what does this now really mean? It means that just by doing fluid mechanics experiments, I can determine the heat transfer characteristics of the plate. So if I would now go and put an electrical heater inside the plate so that it is being heated, I can exactly determine what the heat transfer rate will be. And, or I can do the heat transfer experiments without measuring the force. Just the heat transfer experiments, and then I can use the heat transfer to work towards the fluid mechanics and to get the friction coefficient and the drag on the plate. Now that is very special. Now, I have also distributed to you on Tuesday some additional material. Okay. Now this additional material will most probably be incorporated in the new edition of this textbook, which will come out this year. So it is of critical importance that you actually take this information, that maybe you can make it a little bit smaller on the photostat machine, and you need to paste it in the back of your textbook. There are 7 pages where you can do it, because you are going to need it in the tests and the exams. So this is work that was done here at the University of Pretoria by a PhD student of mine, Dr. Marlies Everts. She's a postdoc now, and she will later on also give a few lectures to you. But what we have shown is that for tubes, this Reynolds analogy works perfectly. In the cases of laminar flow, we have showed that the friction factor divided by the J factor, or the average J factor, is equal to 10.109.71 multiplied by the Grashof number at the bulk to the minus 0.215. The Grashof number, as I've said, that we're going to introduce in chapter 9 in terms of natural convection. But if you are curious at this stage, the Grashof number is defined as G multiplied by beta, the surface temperature minus the mean temperature of the fluid, the diameter to the third, divided by the kinematic viscosity square. So it's quite a simple equation. This one for the laminar flow. Then there's another equation which we have showed is valid for the transitional flow regime as well as for the turbulent flow regime. And in this regime, the heat transfer is not a function of Grashof number, because the Reynolds number is just so much larger than the inertia effects are so much larger than the buoyancy effects. And this equation gives the friction factor divided by J Prandtl bulk to the 0.42 is equal to 3.74 Reynolds bulk minus 8066 divided by Reynolds bulk minus 2,320. Reynolds bulk, okay? So it is not such a complicated equation if you're going to compare it to some of the equations you're going to do later on. But this is then the additional material for chapter 6 that you need to get into your textbook, and I promise you in the test and exams you're going to need it. Okay. Then later on there will also be for chapter 8, internal forced convection. You'll see that much more of the additional equations and work has been included there. Okay, now let's do a good example to show you this analogy for tubes. At this stage we are not going to do a case for laminar flow because you haven't done the Grashof number yet, but we're going to do a case where the flow is in the transitional or in the turbulent flow regime. And this case study is now for a tube through which water is flowing. The measured inlet temperature was 19.94 degrees Celsius, and the mass flow rate was equal to 0.0605 kilograms per second. The length of the tube was 8 meters. Not D. Okay. the length L is 8 meters, and the tube diameter is 11.52 millimeters. And the measured pressure drop, so if you've got a pressure gauge there and another pressure gauge there, the measured pressure drop was 4,060.4 pascals, or 4 kilopascals. Okay. So what I'm going to show you now is how can we move from the fluid mechanics to the heat transfer by using the analogy. Fluid mechanics to heat transfer. And I forgot to say the outlet measured temperature is 23.38 degrees Celsius. So we don't know what this heat flux is. It is being heated at a constant heat flux, Q. And except now for the inlet and outlet temperature, we actually do not know anything about the heat transfer. You can also go and guess the water temperature is 20 if you want to. You'll get still the same result. Okay, so let's do it more correctly. The bulk temperature is the inlet temperature and the outlet temperature divided by 2. The inlet temperature was 19.94. The outlet temperature 23.38 divided by 2, and that is equal to 21.68 degrees Celsius. Okay. Now if you go and look in your textbook, you will see for water in table A9, before the end of the semester you know table A9 very well, and you will see that you can get the properties there, but you can get it at a temperature of 20, 25, etc. So there's not a value for 21.68. In the exams and tests, yes, you can use 20, you can use the closest value. So the properties at the bulk temperature is that the density is equal to 997.8 kilograms per cubic meters. The viscosity is equal to 9.626 multiplied by 10 to the minus 4 kilograms per meter second. The Cp value is equal to 4.1817 kilojoules per kilogram Kelvin. The thermal conductivity K is equal to 0.6044 watts per meter Kelvin. And the last one is the Prandtl number is equal to 6.6572. I will repeat these values. The density is 997.8 kilograms per cubic meters. The viscosity is 9.626 multiplied by 10 to the minus 4. The Cp value is equal to 4.1817 kilojoules per kilogram Kelvin. The K value 0.6044 watts per meter, and the Prandtl number 6.6572. So the Prandtl number of water, order of magnitude, is about 10. Okay, so let's start with the mass flow rate. The mass flow rate is equal to rho AV. The mass flow rate has been given, it's been measured with a Coriolis mass flow meter, 0.0605. It's equal to the density, which is 997.8. The cross-sectional area through which the flow occurs is pi divided by 4, multiplied by the diameter, 0.01152 squared, multiplied by the velocity v, which is the only unknown. So from this we can solve the velocity is equal to 0.5817 meters per second. Why do we need this? Because we want to calculate the Reynolds number. The Reynolds is rho v g divided by the viscosity. Later on in chapter 8, I'm going to show you that you can write the Reynolds number directly as a function of mass flow rate, so that saves a lot of time, that you do not have to go and calculate the velocity. We will get to that a little bit later. So the Reynolds number is equal to the density, which is 997.8, the velocity, which is 0.5817, the diameter, which is 0.1152, divided by the viscosity, which is 9.626, multiplied by 10 to the minus 4. So it gives us a Reynolds number of 6,946. Yep.
Why is the diameter used in the Reynolds number, not the length of the...
It's an important question. Why is the diameter used and not the friction factor? It is a decision that was taken by the people who originally did the experiments. So if you typically look at the Moody chart, the Reynolds number is based on the diameter. And you will later on see that the length, of course, is going to determine the total pressure drop, but the data has been presented in a form which is being influenced by one or other variable, because it can be d or it can be the length L. Later on, when we get to a plate, you'll see it is the length L. So if we want to be more correct, we can say this is the Reynolds number based on the diameter d. Okay. You get to the same problem when you get to a car. Let's suppose you've got a Ferrari and you want to calculate the Reynolds number over this Ferrari. Equation is easy. It's the density, the velocity, multiplied by a characteristic length and the viscosity. But now the question is going to be, what do you use as the characteristic length? Do you use the length of the Ferrari, the height, or the width? So people that would do the experiments would typically see which one has the biggest effect, and the data would then be based on how that calculation was done. So we are moving towards the Moody chart, where the decision was specifically taken to use the diameter d in terms of the Reynolds number. Right, so there's the Reynolds number. Now we can go and calculate the friction factor, which is 2 times the diameter, rho d, divided by L, density v squared. I think it needs a delta P there, because the pressure drop is equal to half times d rho v squared. No, something is wrong. I think it's like that. Yep. Why is there? Yeah, no, they shouldn't be. Just help me. The pressure drop is equal to half times rho v square L, something like that. Let's just check quickly. That's it, okay? So let's rather do it like this. Okay. The pressure drop is equal to the friction factor multiplied by L of D multiplied by rho v squared divided by 2. Okay, the pressure drop is 4060.4 is equal to the friction factor F multiplied by the length of the tube is 8 divided by the diameter 0.1152 multiplied by the density, which is 997.8 multiplied by the velocity. The velocity we have calculated as 0.5817 square divided by 2. So the only unknown is the friction factor F, which is equal to 0.0346. Are you with me now? Okay. Okay, so this is now the friction factor for the tube that we've obtained through actual experiments. Is it correct? Well, very easy to go and see. You can go to your Moody chart, which will give you your friction factor as a function of the Reynolds number. For laminar flow, there's a straight line on a log-log curve, so it is not really a straight line. And then you've got the case for epsilon of d divided by 0. That's a smooth tube, and the rough tube results would typically be there for different values of epsilon divided by d. Now, almost all tubes that you can buy these days off the shelf are, for all practical purposes, if you go and measure the surface roughness, you will see that there are smooth tubes. 50, 100 years ago, tubes were made by sand casting, and therefore they were all rough. But these days, all hard-drawn tubes and soft-drawn tubes, for all practical purposes, are a smooth tube. So we've got a Reynolds number of 6947. So 6947. From there, you can go and get the friction factor. Let's write there the friction factor from the Moody chart. There's also an equation that you can use for this part, for the turbulent part, to go and get it from there. And there you will find it is equal to 0.033. Okay. So if you compare this 0.033 with that calculation, you will see the error is only 4.7%. So the friction factor that we've obtained is correct. Okay, now let's look at this Everts and Meyer equation of 2018. And this equation says that, and take note, very important, this is now turbulent flow. Because you will see on the Moody chart there's an area there of transition, but 6,947 is out of this area, Therefore, the flow is turbulent flow. And in terms of the equations that I've made available to you, we've got the equations for laminar flow, which is not relevant now, and then the equations for transition or turbulent flow. So this definitely falls into the turbulent flow regime, and then you can say the friction factor divided by J, Prandtl to the 0.42 is equal to 3.74 Reynolds minus 8066 divided by Reynolds minus 2320. So the friction factor we have determined, measured as 0.0346 divided by the J factor divided by the Prandtl number, which is equal to 6.6572 is equal to 3.74 multiplied by the Reynolds number, which is equal to 6947 minus 8066 divided by the Reynolds number, again 6947 minus 2320, and that will give us the J factor as 4.05 multiplied by 10 to the minus 3. Okay? Now the J factor, if we go back to the J factor is a non-dimensionalized form of the Nusselt and the Prandtl number. So the J factor is equal to the Nusselt number divided by the Reynolds number, Prandtl to the third. Okay. That's the standard definition of the J factor. So now we can calculate the only unknown, which is the Nusselt number. So the J factor is equal to 4.05 multiplied by 10 to the minus 3 is equal to the Nusselt number divided by the Reynolds number, which is equal to 6947 minus 2320. What am I writing? Reynolds is 6947 multiplied by the Prandtl, which is equal to 6.65. 6.6572 to the third. And from this we can solve the Nusselt number, that the Nusselt number is equal to 52.7. Okay. The J factor is the Nusselt number divided by the Reynolds number, the Prandtl to the third. The J factor is 4.05 multiplied by 10 to the minus 3. Nusselt number is what we want to determine. The Reynolds number is 6947. The Prandtl number is 6.6572 to the third. Only unknown is the Nusselt number, and we can solve the Nusselt number. The Nusselt number, again, is equal to the heat transfer coefficient multiplied by the diameter divided by K. So we can say it's the Nusselt number based on the diameter, and this is also the case here. This is the Nusselt number based on the diameter. That is how it was derived. And the Nusselt number is equal to 52.7. It's equal to the heat transfer coefficient multiplied by the diameter, 0.01152, divided by the thermal conductivity, which is equal to 0.6044. And that will give us the heat transfer coefficient, which is equal to 2,765 watts per square meter degrees Celsius. So again, do not get lost in all the mathematics and all the calculations. This is about a very simple analogy. And that analogy tells us if we only do fluid mechanics experiments, we can actually determine the heat transfer characteristics. Now we're going to do the opposite. In part B, I'm going to give the heat transfer to the fluid mechanics part. So if you've got the heat transfer parts, can you now actually go and get the friction factor and the pressure drop? Okay, now for this part, we have to do heat transfer experiments because it's from the heat transfer to the fluid mechanics. And from the heat transfer experiments, what you now need to get additionally is you need to get the average surface temperature of this tube. And that has been measured as 22.72 degrees Celsius. So what we want to get now is the pressure drop from the heat transfer results. Maybe we didn't believe these pressure gauges, and we are not actually sure, if it is so accurate. Of course, the Moody chart should help us, but let's just go and check. So the heat transfer rate is equal to the mass flow rate, Cp, multiplied by the outlet temperature minus the inlet temperature, mCp multiplied by delta T. The mass flow rate is equal to 0.0605. The Cp, 4.1817 multiplied by 10 to the third. Outlet temperature is 23.38. Inlet temperature was equal to 19.94. It gives us the heat transfer rate must be equal to 870.3 watts. From the heat transfer rate, we can get the heat flux. The heat flux is equal to the heat transfer rate divided by the surface through which we get the heat. So that is the heat flux, Q dot. The tube is being heated uniformly all around the surface, and the heat flux will then be equal to 870.3 divided by pi multiplied by the tube diameter, 0.1152, multiplied by the length, which is equal to 8. And that will give us a heat flux of 3005 watts per square meter. Therefore, it's about 3 kilowatt per square meter is the heat flux. Let's get the Nusselt number. Already at this stage, we can actually go and calculate the heat transfer coefficient, because we can say that the heat flux is equal to the heat transfer coefficient multiplied by the surface temperature minus the bulk. The heat flux is 3005. It's equal to the heat transfer coefficient multiplied by the wall temperature, 22.72 minus 21.68, so that the heat transfer coefficient is equal to 2,862 watts per square meter degrees Celsius. This was the heat transfer coefficient that we've determined from the fluid mechanics part, and this is now the heat transfer coefficient that we've determined from the heat transfer part. If we compare these two, the error is 3.4%. So for us as mechanical engineers, that's great, such a small error. Let's go and calculate the Nusselt number. The Nusselt is equal to HD divided by K. The heat transfer coefficient is equal to 2,862. The diameter 0.1152 divided by the thermal conductivity of the fluid 0.6044, and that gives us a Nusselt number of 54.56. Again, compare it to that part that we've determined from the fluid mechanics. Okay, the J factor we can then calculate as the Nusselt number divided by the Reynolds number, the Prandtl to the third. I'm going to leave that for you to do at home. We've got the Nusselt number, we've got the Reynolds number, we have the Prandtl number. So you can go and substitute it, and you'll get a value of 4.187 multiplied by 10 to the minus 3. Okay. Then you can go back to the Everts and Meyer equation of 2018. F divided by J divided by the Prandtl to the 0.42 is equal to 3.74 multiplied by Reynolds minus 8066 divided by Reynolds minus 2320. And from this you can go and get the friction factor as 0.0358. From the friction factor, you can go and determine the pressure drop. So the pressure drop is equal to that equation that I couldn't remember, the friction factor multiplied by L over D, multiplied by rho V squared divided by 2. Go and do the substitution, and you will see that the pressure drop is 4,196 pascals, which is 4.2 kilopascals, and the error is 3.27%, about 3.3% in terms of what we've really measured. So you can see that the two analogies or the two equations are actually talking to each other perfectly. Any questions? If not, ladies and gentlemen, then thank you very much, and I will see you again next week.